Welcome back, everyone. I'm absolutely thrilled to have you here for another explainer. Today, we're stripping away all the overwhelming complexities of multi-billion-dollar EPC projects, and we're zooming right in on the absolute most fundamental ingredient of them all. We're unpacking Section 3.5.3.1 to demystify the steel plate. Seriously, if you're stepping into the world of stationary equipment engineering, this right here is exactly where your journey begins.
Okay, let's dive right into this. Have you ever actually stopped to wonder how a simple, unassuming, flat piece of metal transforms into the beating heart of a towering industrial plant? It's a truly fascinating evolution, isn't it? Well, in this explainer, we're going to trace that exact journey. We'll start way down at the microscopic level, looking at the actual metallic recipes and engineering codes, and then we'll scale all the way up to see how these raw materials become massive, macro-level pressure vessels capable of holding hazardous chemicals at crazy extreme pressures and temperatures.
Section 1. The core building block. The blank canvas of steel.
Before we get completely lost in abstract engineering codes, material stress properties, and all that complex math, we really need to ground ourselves in a physical reality. We need to look at what the raw material actually is. And this brilliantly illustrates exactly what we mean when we say plate in the mechanical engineering world. Straight from the steel manufacturer, what the industry likes to call the mill maker, these incredibly heavy, flat rectangles of raw steel are just resting in the yard waiting to be utilized. For a mechanical engineer tasked with designing a pressure vessel, this stack right here is your ultimate blank canvas. It's the literal starting point from which the structural integrity of your entire project will be forged.
Now, in the plant industry, you can't just call up a steel mill, order some thick steel, and hope for the best. No way. Everything is strictly regulated. And that brings us to ASME, the American Society of Mechanical Engineers. To really grasp our source material today, you absolutely must understand that ASME provides the global engineering rulebook. They set the uncompromising safety, design, and material standards for plant equipment all around the world. So when we talk about material specifications coming up, we are talking about their strict, globally recognized, and highly tested rules.
Section 2. Decoding carbon steel. Understanding SA 516.
Now, what's really interesting here is that when it comes to building massive pressure vessels, carbon steel is by far the most common flavor of metal you're going to encounter, and SA 516 is the undisputed industry heavyweight. SA 516 isn't just some random string of numbers and letters either. It corresponds to a very real, standardized manual for carbon steel plates intended for moderate and lower temperature service. When an engineer specifies SA 516 on a datasheet, they are legally binding the manufacturer to provide a material with highly precise physical properties.
Section 3. The grade dilemma. Balancing strength.
Here's where the true art of mechanical engineering shines. It's not just about picking a material off a list, right? It's about navigating material selection and really understanding the critical trade-offs that happen when you slightly alter the spices in the metal's recipe. Within the SA 516 family of carbon steel plates, you'll most frequently encounter two numbers, grade 60 and grade 70. Now, these numbers aren't just arbitrary placeholders. They actually represent the material's minimum tensile strength. So a grade 60 plate has a minimum tensile strength starting around the 60,000 psi mark, which translates to a specific threshold in megapascals if you're using metric units. Grade 70, naturally, has a higher minimum tensile strength. So the obvious beginner question is, why would an engineer just pick the stronger grade 70 plate every single time?
Well, so the crucial point is that higher strength doesn't universally mean better performance in all environments. Think of tensile strength kind of like a game of tug-of-war. Grade 70 can pull harder without snapping, which allows engineers to design pressure vessels with thinner walls, ultimately saving a massive amount of weight and money. Sounds great, right? But there's a hidden cost, brittleness. As the strength of carbon steel goes up, its toughness often goes down, especially in freezing temperatures. Imagine dropping a flexible plastic cup versus a rigid glass cup in the cold. The glass is technically a harder material, sure, but it shatters on impact. Grade 60 might have a lower tensile strength, but it retains superior toughness, meaning it won't easily fracture in low-temperature environments. Selecting the right plate is literally a masterful balancing act.
Section 4. Stainless steel. Specification SA 240.
But hey, what happens when carbon steel simply won't survive the job? Well, we transition to the other main base ingredient in our EPC kitchen. Just like carbon steel, stainless steel has its own dedicated, highly specific rulebook. SA 240 is the exact ASME code section you absolutely must turn to when your project requires chromium and chromium nickel stainless steel plates.
You reach for this specification when you're dealing with highly corrosive fluids, strict hygiene requirements, or operational conditions where standard carbon steel would rapidly rust away and just completely fail.
Now, unlike carbon steel, which focuses heavily on those tensile strength grades we just analyzed, stainless steel plates are categorized entirely differently. You're going to see codes like 304, 304L, 316, and 316L. These numbers don't represent strength. They represent chemical composition variations. You're essentially changing the chemical recipe. For instance, moving from 304 to 316 usually involves adding an element called molybdenum to drastically increase resistance to certain types of severe chemical corrosion. And that L? That stands for low carbon, which is absolutely crucial for preventing corrosion during the welding process. So as you can see, it's a totally different paradigm of material selection.
Section 5. From plate to plant. Building the shell.
Let's move to and see how this builds, shall we? We've spent time analyzing microscopic specifications, chemical recipes, and tensile properties. Now let's zoom way out and witness how this becomes a three-dimensional reality. Our basic building block, that thick, flat plate, is taken into a fabrication shop and passed through immense industrial rollers. It's physically bent into a perfect cylinder. Then, the edges where the plate meets are welded together to form what is known as a longitudinal seam. Once you have a few of these cylinders, you stack them end to end and weld them together along circumferential seams. Through this methodical process of rolling and welding, our simple flat steel plate magically becomes the massive, impenetrable structural shell of an industrial pressure vessel. It's pretty amazing to think about.
But here is a provocative thought to leave you with today. Now that we have this massive outer shell successfully built from our plates, what other product forms are required to finish this complex vessel? After all, a plant can't operate with just closed steel tubes, right? Fluids need to be injected, temperatures need to be measured, and gases need to be vented. So, how do we attach pipes? What about the forged steel nozzles and the heavy flanges? The steel plate is the foundation, for sure, but it's really just the beginning of the engineering journey. We're definitely going to have to explore those other critical product forms next time. Keep learning, keep questioning, and I'll see you in the next explainer.